Hey, meneer. Hi, meneer. Good morning.
Morning, Alan.
How you doing?
Morning. Good. How are you?
Good, good. Thanks for jumping on.
No problem.
Just you and me, by the looks of it.
Let me get out from the other meeting.
Okay.
We have this OCP, another meeting happening, OCP planetary meeting, all the platinum members. Let me get out of that meeting.
Which one's that? OCP, did you say?
Yeah, there's an OCP platinum board members meeting happening.
Oh, right. Interesting.
Yeah, and we are the platinum members, and unfortunately, I represent there.
So you guys are platinum. How much that must cost a lot of money?
Yeah. Yeah, we are the platinum members. I actually drove that platinum membership when
That's about 100 grand a year, isn't it, or something?
100 grand, yeah.
Holy shit.
Yeah, so I drove that, there's a lot of, but I said, hey, let's do that. Because I think we are getting some kickback of, because we do a lot of, you get like 25% back from the booths, and we typically like 6 to 9 guys participate in the OCP. So their registration fee, you got a lot of, free registration for that, So it ended up costing like 30 grand, not bad.
Right. So is it easy for you to justify in Lattice, or do you have challenges?
For the membership?
Yeah.
Yeah, it's easy for us because I think one of the things that what we noticed once we joined the OCP big time right now. I was not Lattice guy before. I was a Dell, right? When I joined Lattice, my first priority was, hey, let's do more things than just OCP, and the LTPI is a big one for us.
Yeah,
We made
that was
huge
great to
money.
get that into
Yeah,
OCP. That's
yeah, we
huge.
made huge money on that. About $70 million, 50 to 70 each year. So that's a huge money.
Wow.
Yeah,
People
so
buying your chips specifically for that.
right. And when you wrote the spec, I was one of the spec writer. So I basically moved the company like, hey, do it faster before anybody else except, do
Yeah.
LTPI. So that
Yeah.
gives us like boost. So there's no challenge if I spend money now.
Excellent. Well, actually, that might be an interesting topic for us to talk about, actually.
Sure.
So I've, since the OCP Regional Summit, I was hoping that you were going to be on because in terms of our system management stuff, so where do I start? But specifically on the system management stuff, the LTPI I'm sort of making as a standard for our universal interconnect, right? So we get rid of all the sidebands. The only signal that we've got other than that, the only static signal we've got is connector present, cable present. So you've plugged a connector in, so you just have a short to ground to say, hey,
right.
there's a cable plugged in, therefore it should be going somewhere.
Right.
And if you can't find through discovery of the system management, if you can't find where it's going to, then there's something wrong with that cable. So whereas if there's not one plugged in, you just say, well, there's not anything plugged in. That's fine, right? So there's just one static signal, and everything else goes over LTPI. Was my over the cable itself. And by the way, the cable manufacturers all say it's cheaper for them to put more twin axes in than to try and accommodate these sideband single wires.
Right. It's easy for them, yeah.
It's actually cheaper for them to make the manufacture the machines that are set up. If all the cables are the same, it's a lot easier for them. So anyway, so that's part of the universal interconnect. But then we've got this my control plane, my system management control plane, I'm trying to do with the free space optics communicating in a torus. It may be doing that a few gigabits per second, like between 1 and 10 would be nice. And I guess that's a case of, do we do that with Ethernet or whatever? And I guess Ethernet in some ways makes the most sense, gigabit or 2.5 gigabit or whatever. And so it all, but basically this is all coming back to your device. So I guess to keep it simple, I wanted to, hang on a minute, can I just look at that? I just had a quite important, the CEO of a company I'm working for just emailed me, so I don't. Let's go this week, and next week we'll be crazy a board meeting. How about June the 3rd? Let me just. Yeah, sorry about that. Yeah, so there's a couple of things that are coming together that I'm trying. So I really wanted to get more meat on the bone of your Avant chip with the. So I wanted an update on how close you are to having that chip with the flash, the DRAM, or the encryption, the whatever it is, all in that package. Is that going to become a reality in anytime soon?
Yes, we're doing the packaging now. So it's going to come soon.
So in terms of engineering silicon, what sort of time frame for engineering silicon?
We're just using the existing silicons, repackaging whole thing.
So, or engineering packaging.
Right. Yeah, engineering packaging. Okay. Yeah, so we are talking with the packaging house. I'm thinking about first samples available between 6 to 9 months.
Okay, so it's still 6 to 9 months away.
Yeah, samples, yeah.
And you already have an Avant chip in that footprint with
we already have an advantage in this footprint. This one is giving more, the one that I talked about is giving the
DRAM.
DRAM plus security plus all those things, extra
And a bit of flash as well, is that right?
It's a flash as well. It is hardware tamper proof, right? It can do attestation, security, all kind of stuff.
Do you have a data sheet on it by any chance, or rough?
I can send you the just high level data sheet. Yes,
yeah, because I would like to know how big is the flash, how big is the DRAM.
I can do that. Yeah, it has a built-in ICE40 also.
Oh, nice. Okay.
It has ICE40 built into that. 2 ICE40 built into that.
Is that to give you the what's for? Is that for the single wire aggregation? Or
one for singular aggregation, one for USB. We don't have a hardened USB, so ICE40 is giving that.
Oh, ICE40 has a hardened USB,
yeah.
or oh, does it really? Yeah. Holy shit! I didn't realize ICE40.
So there is multiple versions of ICE40, so one of the versions has it. So we're using that to get that USB capability. So it's packaging up.
Wow, that's bloody brilliant! Actually, if that's going to have USB.
Yeah.
So, all right. So I'm getting serious about an FPGA emulation platform, right? So I'm gonna talk to you about that shortly. But before we get on to that, there's this IBM Power OCP machine that you and Raptor are doing and Jabil, right?
Right.
So, and you're doing that with Power 10. So is that going to be a reality? Is that being funded by somebody, or is it just being proposed as a spec?
This is So for the power, the BMC is already in the market. So Boeing is using that for us.
Boeing.
Boeing, yeah.
Oh, nice.
Okay, so I can send you the motherboard picture that Boeing is using, right? But
With Power 10.
with Power 9.
With Power 9.
Yeah, it's an older one, but I can send you that.
Yeah, I need Power 10 because I need the
Power 10, yes.
OMI memories. I can't do it with parallel memory.
Okay, you're
so
right, yeah.
so well, what I was so that's being done, but in terms of Jabil's proposal of the Power 10 memory box, that's just a proposal at the moment, right? Going into the spec.
So
or is that being made?
There's multiple things happening on our side, you know. So the Raptor engagement that, you know, the Raptor, Boeing and all those engagement, that's something that Raptor is driving, right?
Right.
We just help them, but we don't do anything for them.
Right.
Okay. And there is a partnership happening with Raptor Solid Silicon, which is basically packaging exercise that I just told you, right? Which will have an ASICs, you know, that have an ASIC SoC, that have an ECP5, that have an ICE42, ICE40. It is basically targeting all AS400, SAP HANA kind of an installation, high security installation, and as well as also for x86 installation. It will be much more powerful than existing BMC.
Much more
powerful than existing BMC that we see. So existing BMC has a limitation about how many nodes you can support. You know, it only can support max 2 nodes, right? This will have a much more powerful than, we don't know how many nodes it can support, but you're targeting to have multiple nodes, like 16 or more nodes. Okay, that's another engagement. And then Avant engagement. So this is, Avant is our internal engagement. It's getting a little bit pushed out because of we are doing some external one. But internally, we're trying to also develop, you know, BMC and F1 base. So far, we have, from the customer perspective, I think Dell EMC is interested on that. We're doing a POC for them. But I think that's kind of like, you know, it's very pushed out because all the other activities happening today, you know?
Right.
Because we're seeing a lot more attraction there, so that's the main thing. But in a nutshell, we are advancing both in the BMC and also do you know what the BIC is, right? What is BIC?
What the
BIC?
BIC? No.
So basically, you know, if you look at that as dense computing, right? Or to a certain extent, you can say high performance computing, right? Not like your design, right? But I'm saying where the dense computing means you have, you know, you have many cores, many memories. And because when Amazon and Google, they rent based on the core, right? So what they do is that in dense computing, they put blade art kind of architecture. So you have many smaller nodes, but none of them has remote management capability.
Right.
But they have all the BMC functions except the remote management.
Okay.
And remote management done is the chassis level, you know. So basically, one chassis can have 24 of these nodes, right? And the remote management can have the chassis level, and these all nodes will have a, you know, something that is BMC but not the full BMC, which is called the BIC,
right?
Which is basically BMC minus remote management, right? So we're doing BIC, but I think ultimately we're targeting to solve that remote management capabilities for all of them, because we don't want a BIC for
so
all
you're
of them.
basically bundling the remote management into the native BMC itself, effectively. Nice. Well, that's. And so when you say you're doing that, does that mean you're putting Wi-Fi into it, or is it just an Ethernet port?
Ethernet, just Ethernet. There's no Wi-Fi.
And so will that be part of this multi-chip package?
Yes. Yeah, definitely has to be. Has to be.
Really? So can I have 4 or 6 Ethernet?
I can give you some. Yeah. Okay. Once I get that, I can give you definitely some samples.
No, I'm not about that. Can I on your new device, can I create 6 1 gig or 2.5 gig Ethernet ports? How many? So you'll have a hardened Ethernet in there, I guess.
We haven't hardened Ethernet. You need
But it'll
6,
only be
right?
one, I guess.
Yeah, there's only one right now. Still,
And that's inside the Avant chip itself, is it?
that's a yeah, it's a 10 gig Ethernet port.
Oh, it's 10 gig, is it?
It's a 10 gig, yeah. So
let me just.
why do you need six of them?
Well, yeah. Well, ideally, that would give you a torus. That would give you a 3D mesh of what I call the. So I'm thinking that the system management. So a minimum of 4. Let's just say let's go with 4, right? But 6 would be nice. But basically, what we do is you make this humongous machine. Effectively, you've got nearest neighbor. You connect your system management in a mesh to the nearest neighbor, and it's a lowish speed. I mean, it's highish speed, but low relative to the data plane.
Right.
And you don't basically, instead of keep routing everybody to a big switch, everybody is a switch, but they're a switch for 4 ports. So it's like back in the old transputer. So what happens is you've got your Ethernet packet comes in, and if it's for you, then you service it for you. But if it's for somebody else, you just send out the correct port to make on its journey to whoever it is. And because it's system management, right? So you have this mesh going in, and at the edge of the mesh, you can either have just one single port being your main input to your console, or you can have multiple inputs if you needed more bandwidth into the big network. But the idea would be is that, I mean, that's the principle of what I'm trying to do here, to keep the physical architecture nice and simple on the control plane level. So effectively, I want to raise the BMC, the 1970s A-speed BMC technology up to today, and actually let's play it catch up so it can be a control plane system management. So it's literally managing all of the aspects of keeping the machine healthy, making sure the machine's healthy, making sure the machine's secure, all of these, which are becoming quite serious aspects. They're relatively performant in their own right compared to the 1970s I2C bus. So if we actually, so I'm just trying to think forward to that. So it sounds like you've got everything in this Avant chip, this multi-chip package.
So if you have the 4 ports, right? Alan, for example, 4 Ethernet ports.
Yes.
So you have a BMC here. I'm just trying to understand architecture a little bit, right?
Yes.
You have a BMC, you have 4 Ethernet ports, you have a switch coming from, right?
Well, inside the chip itself, you'd have the switch. You'd have a 4-port switch in your Avant FPGA. So effectively, you could either just have, if you had 1 gigabit, only 1 or 2.5 gig, let's say. It doesn't need to be 10 is my perspective. Now, we may want to analyze.
So let's assume that you have, okay, whatever, 2 and 5.
Well,
and that switch is servicing what? Who?
Well, I didn't understand that. Just like you're already putting 1 in, you're putting 1 10 gig one in, which you're using for your remote management, right? So that seems like a big overkill for remote management, 10 gig.
Okay, yeah.
Right? I mean, maybe I'm wrong.
It's basically because you don't have, there's, we don't have option. We can make it 1 gig, but there is already 10 gig available, so it doesn't matter to us,
Yeah. And if you're hardening it, it's probably relatively small.
Yeah.
But yeah. So to that point, it's like, well, I mean, in my mind as well, if your select IO can do 1 gigabit per second, it's a case of you could maybe do it very cheaply if it was 1 gig. Is the other thing? It's all about cost as well, right? Relatively speaking. And so, but basically, you would have the switch. So you'd want 4 or 6 gigabit Mac engines, which I guess use up a fair decent amount of space if you're doing it with logic. So if your 10 gig Mac could also turn into 4 or 6
Or
1 gig.
2.5 gig, yeah, for example.
If it had the ability to service 6 1 gig Macs, which is less speed than 110. So I don't know if you can design a Mac like that, but if you can. But then as well, if it also had the feature of a switch built in there as well, that basically you've got your IP address for the chip itself. For the Avant chip, it's got its own IP address, and obviously if the traffic coming in from whatever port is for it, it takes it and deals with it. But if it's for anyone else, for the various tables that get loaded in, it routes it out the appropriate port to make its way to the destination. So the switch is a very simple 4-port switch or 6-port switch. And every single device has that 6-port switch natively built in. So it's power efficient. And then we literally, and in my mind, you know, we can drive these free space optics. Like Avicenna can go up to, like, they're starting at 4 gigabits of these flashing blue LEDs, right? So we can do 2.5 gig Ethernet with a single LED. Maybe we do a mesh of 4 LEDs for reliability, you know, or whatever. So we can talk to you know, Avicenna about that, but or others. You know, it doesn't need to be Avicenna, but basically LED technology, and that will give us this free. There'll be no connectors. Nobody needs to plug in cables. They just mount the module, and instantly they'll be talking to their nearest neighbors. Is the idea. And
typically, like you know, sometimes like we do this is a VLAN. I don't know if you're familiar with VLAN or virtual LAN.
Oh, right. Okay. Yeah.
We do sometimes something like that. You know, I'm not. You know, I still need to understand a little bit more about application. But from the VLAN perspective, what VLAN does is like the first thing VLAN does is like, if you look at the switch, right? Switch goes, as I said, data plane, then management data and IO data and all kind of stuff, right? So the switch actually first thing it does, it cuts off that, you know, and that well, application actually, you know, says that, okay, this is a VLAN ID 1, this is a VLAN ID 2, up to 256 VLAN IDs. So when switch that, they knows immediately that, okay, this is the IO data, this is the management data, for example, right?
Okay. Yeah.
And the BMC gets that, and the BMC can also incorporate some VLAN, and it can transfer the data itself, you know.
Right.
It can assign more VLANs, you know, as it says. But let's talk. Yeah, I think we can talk about that.
Okay, well, so I guess there's a potential, depending on the IOs you've got available and how they can be. By the way, they don't need to be. The other thing is they don't need to be Ethernet. We don't need the magnetics of the Ethernet if we go optical, right? So we just need a 1 gigabit signal, but either a transceiver 1 gig or just regular IO 1 gig, driving an LED. They can do a short reach link to its neighbor across on the other side, a couple of inches away. So that was my thinking there. Anyway, so that would be a nice. Now maybe I don't know how much soft logic we would need to build that relative to how much that Avant chip has got.
I need to look at that. Yeah.
But that would be another way of doing it on the basis we don't have it hardened in your Avant, and then we can make or you can make a decision if it does begin to get interest and traction as to whether it's worth hardening it into the device in the future.
Sure.
Anyway, but back to the so I've got this view. If we already have a Power 10 open source design in OCP that Jabil are doing with Raptor, and if IBM or Open Power are helping out, if Meow is directly involved with this as well or not?
Who? Yeah.
Meow is the head of Open Power. She's a president of Open Power.
No, she's not. Yeah, it's basically Todd Rosedale and all those guys. Yeah.
So it's Todd that's driving it, right?
Todd, yeah.
Well, Todd knows all the IBM people, so he can.
Yeah, he knows.
He's the one that knows if he can get the data out of IBM to build this machine. So all I was thinking is if all that data is open sourced to OCP for Todd and Jabil to build this server, then we've also got that same information for us to just repackage it into an HPCM module, right?
Yes.
And the thing with our HPCM module is it's small, right? So we don't have the real estate that he's going to have. So we got to make sure that we do pack everything in. So your Avant chip is critical with all of its memory, flash and memory features. And so my first question is, can I build a Power 10 with your Avant chip? And do you have enough DRAM, enough flash that Raptor's doing in discrete ways with the current build? Can you take what Raptor's doing right now for Power 9 for Boeing and maybe Power 10 for Jabil? And will you be able to identically repeat that in this Avant package with all the flash and DRAM in it? Will we be in a position there's enough flash? Like he uses a 16 gig flash. Your chip only has a 1 gig flash. We're screwed, right?
Yeah.
That sort of thing.
I'll need to look into that. Avant has multiple versions, but yeah, let me look into that now.
But so I guess my idea is maybe I can revisit IBM in Power with regards to Open Power, with regards to making an HPCM module if all this data is already going into make a
yeah. So from our perspective, right? There is no, so the BMC system management itself is a complete, separate solution. It's a different computer itself.
Yes.
If you look at truly, because it has its own power sequencing, it has its own DRAM, it has its own operating system, it has its own e-boot and everything, right?
Yeah.
So the thing that it needs to do, remote management, it has its own Ethernet to do the remote management.
Yes.
That's very common from whatever is IBM or Xilinx or x86, it doesn't matter, right? The sensor management is also very common because you have the same sensors across IBM systems as well as other systems, right?
Right.
What is difference is that the main difference is that IBM has an FSI interface.
Yes.
Which means that Intel has an ME interface. AMD has something different, right?
Okay. What does Intel have?
Intel has ME, management engine, ME, management engine interface.
So you've got to be compatible with all of their interfaces.
Right. So we need to have like some kind of IP developed where if we go this for, if we go this for PowerPC, you need this FSI compatibility. And because you need to talk to the CPUs for the management, right? But everything else is same.
But ideally, what you do is on the one front, you've got to do everything for IBM, Intel, AMD. But on the other front, you want the OCP version that anyone new has this fully open sourced version.
Right. Yeah. So I think we see that this way that, hey, remote management doesn't matter what system you have. Sensor management,
the FPGA allows you to fit into everyone's world right now.
Right. Yeah.
While you try and herd the cats into one open standard. Right.
So that's what we see that way. And that's the reason we said, okay, we can build, and for us it's easy change, to go FSI, ME or XO or anything that we do, it's easy change for us, right? It's not a big deal for us.
Right.
So that's what we're trying to do. So to us, it's not a big deal whether it's a Power 9 or x86 or whatever it is, right? As long as we have the base cores are available.
Well, by the way, that's my point on these HPCM modules. Again, the beauty of your device is that I can do exactly that. We can put
any kind of CPUs.
And by the way,
do any CPUs.
So I'm putting so this first emulation project is I'm putting the biggest Xilinx FPGA down, right? AMD FPGA. And that's a VP1902. And that's got its own sort of system management engine inside as well, right?
Right.
And you can talk to that through USB. By the way, USB is one of the ports into it, right? As well as and it's got its own flash, and it's got several pieces of its own stuff, right? And I'm sort of wondering so this is where it's a bit of an exploration with me and Xilinx, AMD, and I mean I'm from that world, right? So I certainly know how they used to do it. I was involved in their gradual migration to the SoC on chip. So I'm aware in general of what it can do, but it is this sort of Swiss Army knife of an SoC. But I just want to make sure we can do the effective booting of that device in a performant way for various reasons, bring the device up with a bit stream. But the thing that would be managing it is this BMC. The BMC would have that, right?
Right.
And so bit streams, secure bit streams would have to come in maybe through the system management ports, right?
Yeah, secret bits, yeah.
And so you would boot this thing up. You wouldn't really want onboard flash for the bit streams anymore. You just want an onboard flash to be able to boot the device. And I'm pretty damn dogmatic that we really do, with our systems getting so complex and our security getting so complex, you really do want a separate chip, which is, to your point, to your Avant chip, right? Which is separate power domains, separate reset domains, separate everything. And so effectively, that is common, or at least it's open source common. It ultimately can be different vendors, right, as the world moves on. But ultimately, when you plug these modules in, this heterogeneous machine, however it's built, it doesn't even need to be built our way. These processors, these management processors, boot up first, and the big ass power hungry, bloody expensive stuff doesn't even get turned on. It's like you turn the machine on, all these little processors come up, they all talk to each other, and they have a conversation, a security conversation, a boot conversation, a discovery conversation of, shit, I got 10,000 GPUs, 5,000 FPGAs, 2,000 CPUs, and they're all wired together like this, right? So the system management becomes one major sophisticated machine that is really taking care of the health and all of the security and everything
security aspect, yeah.
And all, power monitoring, thermal management monitoring, these are critical now. Power and thermal management are absolutely critical in the control loop of, shit, we're burning too much power here. We're consuming 20 megawatts and the power station's only got 10 megawatts. So, we have to back everybody off,
But the key thing, as you said, right? Yeah, because we had the power separation, as I mentioned, right? BMC has to be power separated.
It has to be power separate, yes.
But it will only allow system to boot up if it is secure enough, if it is authenticated.
Yes.
Right? And then once it is boot up, then you have all the power management, all those things to come up. Your thermal management. Initially you don't need thermal management.
So you say, hang on, I've got a device here and I can't work out the root of trust of this big device that I've got attached to me. Right. Sorry, I'm not going to boot anything up. Yeah. Red flag. Until you sort out what this strange thing is connected in the network, I'm not doing anything. Right.
Right.
So I'm a big and the only view that I've got here is potentially this system management control plane could sort of also have a sort of a control layer to it. It could do work. This is sort of where it could synchronization work. I think there's a synchronization engine that we need to keep all of these tens of thousands, hundreds of thousands, millions of processors. At some point you want synchronization so that they all work in harmony. And so I sort of see that this processor can also be a synchronization manager.
So this is another good point, right? This is what I thought a long time. So I'll give you my feedback on this, right? So typically, the way we do these things, synchronization, is a much worse way. And I'll tell you why. So you have a rack, right? You have a rack, and each rack has a limited power. 3 kilowatt, 4 kilowatt, 5 kilowatt, or 10 kilowatt, whatever it is, but it still has a limit.
Yes.
It cannot go but beyond that limit, right? Right. So either you over provision, but how much over provision you can do? There's no limit, right? The problem is that in a rack environment, people go change the racks all the time, right? Or they added the GPUs. So what happens if the rack is overloaded, all the server shuts down. There's no way to control that because rack cannot provide that much of power, right?
Right.
It has a big data loss situation there. And the boot up all the servers, you're talking days of exercise.
Yes, yes.
You're talking days of exercise, right? So the way we do that today is we try to be over provision everything, right? So what you do is we control the power. Hey, initially we set it up CPU. This platform is designed for, say, 700 watt. Even though the max power can be 1400, we throttle the whole thing down, right?
Yeah, and if you're in control of the clocks, you can say, "Well, run the clocks at half speed," and you
we
burn
throttle
it.
the whole thing down. BMC does the whole thing down. But then the problem is that there is no mechanism of BMC talking to other BMC in the rack.
Well, that's where this mesh is.
Yeah, so if you have
each of
that
us can talk to each other.
capabilities, if you have that capabilities, then you don't need to throttle. You may see that some other node is.
By the way, another thing on that's brilliant. So another thing on that is when you run an application, it's a case of you're always waiting for somebody. And if you're running everything at full bore, but this one's finished and this one's waiting to start, it's like you could, well, I can wind this one down because it's waiting to start. And this one, we're waiting for this one. Let's put this into turbo. And once he's done, wind him down and then wind him back up. And so you could have it again at a system synchronization level. You could be seeing the profile. If you could do a runtime profile, you can actually hand the power around to where it's needed.
Plus, you don't need to throttle sometimes because maybe you have other nodes that is not working, that is not working full time.
Right. So we're it's lovely. We're on exactly the same page. So and you're marching lovely. You've been doing it for ages, but you're marching in the right direction. It's completely my view. And so and the thing is because everything's shrinking anyway, and we want to get it into a Lego brick type scenario. Obviously space is a premium, so your package part is great. But getting all of that in, so I'm sort of turning to this emulation platform. So maybe in the time we got left, I was going to give you the big picture of I'm driving down to an application now. And by the way, I don't know if your Boeing friends might be interested in this, depending on what they're doing with Raptor, but what I've come to realize is emulation is becoming a bigger and bigger need. Is these chips? So these chips are, they're like H100's 80 billion transistors. You see TSMC are now doing wafer scale. We've got Cerebrus's wafer scale, one massive chip. And we've got Tesla Dojo, which is like known good die being put back into the wafer, and then RDLs, redistribution layers, connecting it. And TSMC are productionizing the Dojo approach of Tesla for everybody else. So I can see that some of these guys are going to be getting to the wafer scale level, right? And these are like, at the moment, they're like 15 to 20 kilowatt, where a 15 kilowatt, I think is a wafer scale power right now. And so where I've been beginning, and people have been saying, as these things are getting bigger, have we got the right size module for HPCM? And I was thinking, well, actually, we've got a very nice setup, and we could put two HPCMs together if you needed a bigger chip and you needed more power. But we could probably put 6 HPCMs in a 2x3 grid, and we could actually plug in a wafer, if your wafer unit you could scale up that you could plug in a wafer unit at the end. But the thing is anybody designing these things, they're massive amounts of money, right? And it's all about building domain specific computers. And, I presume you followed the term. Hennessy and Patterson drove this, or made it common lexicon of this is what we now need to do in the world of computing, is domain-specific computing. And they said it in their Turing lecture 5 or 6 or however many years ago now, time flies. But they've just coined a term that was already in existence, especially if you go back to the 80s, that's all we did. And if we look at HPC, really HPC is a domain-specific computer, because classic HPC is what you call nearest neighbor. So when you're modeling the weather, you've got atoms knocking into each other. So you have this 3D mesh architecture. So mesh is popular for HPC, because it's all nearest neighbor. It's atoms hitting each other, and you're modeling the world. And then you do a torus, like of the world, because the world wraps around on itself. So therefore, you've got the torus that when you get to the other side, you wrap everything around. So 3D torus architectures for HPC is the classic HPC. And then when you do nuclear physics, it's atoms hitting each other. So it's the same model. When you do, what's the other one? QCD, quantum chromodynamics, it's the same. So a lot of the classic HPC, so the HPC was the world's first domain-specific computer. And I sort of worked that out when I was young, in my teens even, when I was working on this. I couldn't understand why they were doing these stupid mesh architectures when our computers needed something completely different. And that's the first domain-specific computer. If you look today, and then we've got domain-specific chips like FPGAs and GPUs, so they're doing it at silicon level. But if you look at AI today, AI is rapidly going down many different domain-specific avenues, where somebody thinks they've got a better avenue for it than others, right? But it's such a huge market that everybody's going down in that direction, and they're throwing the money at it. But there's a whole horde of applications between the two that are relatively decent markets, but can't justify the massive investment of AI or HPC had for that domain specific.
Right.
And except for maybe at the IoT level, at the IoT level, you're building it for one little market, and it's a fairly cheap chip in this fairly high quantity because there's so many sensors. So that makes sense. And you've got lots of domain specific IoT. But for example, computational fluid dynamics that I worked really hard with GE back 20 years ago on the FPGAs, is an extremely complex heterogeneous code. And the big pieces of software that take the most time, there's 3 pieces, which we accelerated with GE. But if we could infinitely accelerate those 3 pieces, we'd only get 2x acceleration, because the other 15, 20 pieces were dominating the runtime. So you need to accelerate everything, right? So you really need a heterogeneous domain-specific computer for CFD. Now, CFD is a massive market as well, especially with this thermal management and all the rest of it going on, finite element analysis, aircraft, and GE are everywhere. So for me, I think CFD is a nice mid-size market that would benefit from a domain-specific computer. So that's my for my frontiers proposal, I'm saying that we want an example application of where HPCM, my wall of compute, might make sense, and that's CFD. Because people keep asking what application, right? And then there's the emulation piece of this, which is like a digital twin. So you use the buzzword digital twin.
Yep.
And so Paul Hartke at Xilinx said that digital twin is a more of a catchword than emulation, ASIC emulation. So if we built, so I worked out the number of the big FPGAs from Xilinx to make an H100 80 billion transistor is about in the order of 30 FPGAs. So you'd want 30 FPGAs connected to the way you want your ASIC connected to do one big emulation. If you were going to do a wafer scale emulation, like with 25 of these chips, you need about, I think it was about 400 of the biggest Xilinx FPGAs to emulate one wafer scale from TSMC today. So our wall of compute would allow you to build this in an emulation form, and you could cable it together the way your ASIC emulation needs to be cabled together, right? But then as you now then they might say we're going to build a dedicated chip for this piece of the CFD flow. And so then you might have a real chip, or you might be doing chiplets because chiplets are coming in. And so what you can do is you can bring real chips into the emulation so that you got this entire FPGA emulation. And then you get a real chip come along and you say, well, okay, we're going to make an HPCM module with our real chip, and we're gonna put that real chip in to the rest of the emulation. So you have one real chip with the rest emulation. So we did this in the 1980s and 90s in the British aerospace when we were building missile systems. We had software simulations on the big VAX machines of the whole missile system. And then when the guidance and control people actually got a design of like the imaging head or the navigation, they actually, we unplugged the simulation and we put in the real hardware with the rest of the simulation, and we called it hardware in the loop. Right? So effectively what I'm saying is we have this big emulation thing, and then we gradually replace the FPGAs with the chiplets with FPGA interfaces into it, right? And by the way, this is something that maybe Lattice might be interested in, is I'm not sure what chiplet avenue you're going down, but if you could bring chiplets into the FPGA emulation world, you know, it might be a Xilinx emulation because they do the real big devices, but if you could actually be a bridge to bring, you know, a real chiplet with a bunch of wires or UCIe into the FPGA world, and then we can connect it into the bigger FPGAs, then that can be part of the strategy. So, but what happens is somebody like GE starts to build real ASICs as they do, and they've got a plan and they're emulating everything else. And as it comes together, they're proving that the real chip does the same as the emulation did. It gives the same answer until you've compiled everything and you've got all the chips in HPCM format, and there is no emulation. And then you say, well, now we want to take all these chips and just pack them all in one package or one wafer scale. And then we've got our production ready domain specific computer for CFD that's 1,000 times quicker than using GPUs, or whatever, 100 times quicker than using GPUs. So I'm going to say in my frontier proposal, we're building a digital twin for supercomputer design, for domain-specific supercomputer design. That's the headline. And we're going to do CFD as an example use case of how it could work. And I'm hoping to get GE involved because they have their own CFD code, and that is a huge part of their world. And they used to be in computing back in the 80s and 90s, if you remember.
Yep.
And they've got a very, very smart computing research group that worked with me on the FPGAs. It was my biggest project for a number of years in the early 2000s. And they're a genius bunch of guys. And so I pull them in, and then hopefully I can pull companies like the one I'm contracting for, Next Silicon, with their new compute chips, you know, people that think they've got a nice compute chip, and if GE are interested in it, then that'll be good. Or others, you know, Grok or whatever. And if we can begin to pull people in, so that's what I'm trying to get done. So the New Frontiers proposal, by the way, that it's going to land. It's going to land sometime towards the end of June, and we're going to have 4 weeks to get our response in. So what I'm trying to do is I'm trying to get that story I just gave you. I'm trying to get that into the proposal. I've given myself a lot. So I want to do that quickly. And I'm trying to fill in the different sections, like the system management section as well. And our conversation today just gives me great enthusiasm that basically you and I are on the same page, that we're saying this system management needs to be much more sophisticated. It needs to be its own compute engine, quite capable, separate power domain, it boots up first, is completely independent of the rest of the stuff, completely trusted, and then it can pull in these heterogeneous pieces and say,
Yeah.
I trust you, I trust you, I trust you.
If I don't trust you, then you're out.
Right, right. And so to be honest, I mean, if in the system management section, because we are so on the same page, I mean, if you could give that boilerplate of the story of where system management can go, which clearly Lattice, you're on that path already. If you can help me describe that in the system management section, then that'll be good, because
I can, I can do. I think I have a much bigger vision there, so I can definitely do that.
Yeah, if you can paint that vision into that section. And by the way, we got to remember, this is a DoD, this is Oak Ridge National Labs. They really want to have a completely open platform in that sense. And, you know, each of these proposal pieces, as well as I want to get to a position of where they go, I don't really have a system integrator still that I can really say is good to do this. That's where I'd love IBM to be in the picture, but that's tough. But GE, maybe GE can persuade IBM that they want to do this. So, and so it all depends on whether GE want to do it themselves. Maybe GE say, hey, we're going to be another IBM again. We're going to build computers again. So maybe they want to do it and could be the system integrator. But the only thing is irrespective, if we can get this proposal right, the system management, the thermal management, the interconnect, the universal interconnect, etc., I want them in the proposal to be standalone, attractive. So if it catches the DOE, the Oak Ridge National Labs, New Frontiers imagination, they go, hey, we'll fund that little piece, but we won't fund the rest. Or we'll fund these two pieces, but we won't fund the first. Ideally, it would be great if they say, we'll fund the whole damn thing. But maybe we can get a couple of cherries out of it to take us in the right direction. So
hey, Alan, I think we have to, yeah, let's have another meeting on this one, okay?
Okay.
Okay. I think I have a couple of bits. I have a customer meeting now, so I need to be a little prepared.
Yeah, no worries, no worries. But
let's have another meeting. Yeah, I think we need to have much more discussion on this. It's not. Yeah, I'll tackle this. Management side. I'll put together some thoughts on that. Just a very rough thought, but then we can flourish more.
Yeah, and if you want to, depending on how you want to either enter it directly, or if you want to write it separately, and then just
I'll write it separate. I'll send it to you, and then we can go through that before we put something in the documents. Okay.
That sounds good. That sounds
great.
Thank you, man. Talk to you. Take care. Bye. Bye.